Hi everyone, I just wanted to take a few minutes to go over the calorimetry lab with you. The first thing you'll find in the lab folder is a link to a YouTube video that goes over the basics of calorimetry and some of the calculations. So hopefully you'll find that useful if it's been a while since you've gone over some of this stuff in the lecture portion. Next thing you'll find is the experiment sheet and the report sheet, as well as a place to turn it in. So this is another lab kit lab, so it's a little more involved than some of the things we've been doing. So I just wanted to go over some of the details with you. So what exactly are we going to be doing? So we're going to be using a coffee cup calorimeter, which is exactly what it sounds. It's a calorimeter made out of a coffee cup or any type of styrofoam cup. And you're going to be using that to determine ultimately the specific heat of the metals used to manufacture pennies. So we're going to find two things. We'll find the calorimeter constant for your homemade calorimeter, and we're also going to find the specific heat capacity for the metals used to make pennies. We can skip this second half of this heat of reaction of the acid-base neutralization, so I just want you to do these first two steps. It's essentially the same thing, so I think it's a little bit redundant. So what exactly are we talking about? We're talking about changes in enthalpy, delta H. Okay, so if we take a look at this reaction, so we have hydrogen combining with oxygen to give us water, so the formation of water. And we can see that the delta H value is negative, so it's minus 572. Not so interested in the value, but more that it's negative. So what this means is, if I have a negative delta H, that means it's an exothermic reaction. So that means that heat is given off. If we had a positive delta H, that would be an endothermic reaction. That would mean we have to put heat in. And generally, we see that this is exothermic, and that's generally true for forming bonds. So if I'm breaking bonds, I usually have to put energy in. If I'm forming bonds, I usually release energy. Okay, so we see that the formation of water is an exothermic reaction. One way to measure this type of thing, or to measure the energy change, so the enthalpy change in a reaction, is by using a calorimeter. So a calorimeter is just a device used for measuring the changes in heat of a reaction. Okay, so generally speaking, you carry out a reaction inside the calorimeter, you measure delta T using a thermometer, and then from there you can calculate the heat of the reaction. So we're going to assume that the heat of the reaction, Q, is equal to the heat of the solution plus the heat of the calorimeter. And again, Q of reaction is the heat of the reaction. Q solution is the heat absorbed by the solution, and in this case it will be water. And then Q cal is the heat absorbed by the calorimeter. Okay, so in other words, what we're doing is we're looking at how much heat does the water absorb and how much heat does the calorimeter absorb. Add those together, that will tell us the entire heat gained or released by the reaction. Okay, so the heat absorbed by the solution is calculated from this formula. So we have Q of the solution, which will be equal to the mass of the solution, and that will be in grams. So you'll find the mass of the water that you add, and generally we can use the density for this, times C, which is the specific heat for water. So this is C applies to the solution, so it's the specific heat of the solution, times the change in temperature, the delta T. It's worth noting here that delta T is equal to T final minus T initial, assuming that the heat has increased. And that's generally what we're going to see in this case. So take the final temperature and subtract the initial temperature. The initial temperature being the temperature before you add anything. Okay, so in this case, we'll be adding, in the first step, you'll be adding hot water to cold water. So the initial would be before you add the cold water, or hot water, excuse me. And the final will be the maximum temperature after you add the hot water. Okay, we'll touch on that again later. Now, we also want to know the heat absorbed by the calorimeter. In other words, we want to be able to calculate C cal. Okay, so this is a little bit different than specific heat, because specific heat refers to a specific substance. So think specific substance, specific heat. So in this case, capital C, so notice specific heat is lowercase c, capital C refers to the heat of the calorimeter. Okay, so the reason it's different is we call this heat capacity. And the big difference is that heat capacity refers to an object. So because our calorimeter is not made out of one specific material, it's going to be made out of styrofoam and cardboard. It's not one particular thing. So we can't calculate a specific heat for that. What we can calculate is a heat capacity. Okay, so heat capacity is essentially the specific heat but for an object. Okay, well, I'll show you in a few moments how we calculate this QCal. Okay, so moving on. So the solution, and this is going to be water, has a specific heat equal to 4.184 joules per gram degrees C, and density of 1 gram per ml. And that's simply because we're referring to water. If we're using a different substance, these values would be different. Okay, and the final heat of the reaction, delta H. Actually, we will skip over that sentence because it has more to do with the actual chemical reaction rather than the pennies reaction. So let's just move on from that. Okay, you can go over the supplies you'll need. Mainly you'll need water, pennies, a styrofoam cup, and this can be either from a fast food restaurant or just if you have a small coffee cup at home, that will work just fine. You just want it to be a styrofoam cup. A piece of cardboard, that's for the lid. If you don't have cardboard, you could use something similar. Spoon or tongs, that's to pick the pennies out of the hot water. Towel, just to clean up any extra water and to pour the actual hot water. You can also use an oven mitt if you have one that's kind of grippy and won't spill. Just be careful with that. You'll need your thermometer, your digital balance, and your graduated cylinder, as well as your hot plate, beakers, tap water. You don't need indicator, vinegar, or calcium hydroxide. That's for the acid-base neutralization. Okay, so let's look at a few things here. So they give us the specific heat of the pennies and the specific heat of the water, as well as the density of water, the density of vinegar, and the density of a calcium hydroxide solution. We won't need those last two numbers, but these first two numbers and the density of water will come in handy. So what is it you're actually going to be doing? So first answer the pre-lab questions, and then we will construct your calorimeter. So what you want to do is you want to clean your styrofoam cup, unless it's already clean, and you want to place 150 mLs of water into the styrofoam cup. And then you want to cut the cup approximately 1 inch above the water, and then you can discard of that water. Or you can reuse it for the next step if you'd like. Then you want to cut a piece of cardboard large enough to cover the top of the styrofoam cup. And it's best to have it overhang a bit, just so that you get a good lid there. You want to cut a small hole in the center of the cardboard for the thermometer. And then you want to assemble the calorimeter. Okay, and then here they're using the actual blue cap of the thermometer to suspend it so that it doesn't touch the bottom of the cup. So it's important that it doesn't touch the bottom of the cup so that you're measuring the heat exchange or the heat of the temperature of the water and not the temperature of just the cup itself. That will hinder your measurement there a little bit. Okay, so here's your basic setup, and if you're using just a normal styrofoam cup at your house that you might have for coffee, something like that, just make sure that it's big enough to hold this volume of water. If not, maybe run to a fast food restaurant and get a cup from them. Okay, so now that we have our calorimeter constructed, we need to first measure the heat capacity of our calorimeter. So how will we do that? Okay, so the first thing you want to do is you want to measure 50 ml of water into a 150 ml beaker. You then want to heat this water to approximately 40 degrees C. And notice it says approximately because we're going to be measuring the temperature of the water, and all we need to know is the exact temperature it is before we add it to the calorimeter. Okay, so just around 40 degrees C. It doesn't have to be exactly, but just make sure you know exactly what temperature it is before we add it to the calorimeter. The next thing, you want to measure the mass of the calorimeter. Okay, and you can do this separately if it's easier, if it doesn't balance quite right. But if you can get it to balance, you can just put it on all at once. Or again, you can measure it in parts and then add them together. Then you want to pour 50 ml of cold water into the calorimeter. In other words, this will be the temperature of just normal standing water in your house. So this can be just your tap water is fine, whatever temperature it comes out at. Okay, then measure the mass of the calorimeter with the cold water and allow it to reach equilibrium for 15 minutes. In other words, allow it to reach room temperature as closely as you can. Okay, so in that step, we are wanting the calorimeter and the water to be the same temperature. Okay, and then that'll kind of give us an idea where the calorimeter is starting out from. Oh, what did I do? I'll jump back to the top. Okay, so allowing to equilibrium, allowing it to reach equilibrium will allow us to know that the temperature of the water and the calorimeter are exactly the same. Next, accurately measure the temperature of the cold water and record it in the data sheet. So that'll be our initial temperature of the water and our initial temperature of the calorimeter. Next, accurately measure the temperature of the hot water in the beaker and do this immediately before adding it to the cold water. Next, add the hot water to the calorimeter. And remember to place the lid on, and you want to record the temperature every 10 seconds for 3 to 5 minutes and watch the temperature reach an obvious maximum. So record the maximum temperature and make sure to swirl the calorimeter while taking the data. In other words, make sure you stir it. Okay, so the reason you're doing this is so that you want to record, or because you want to record the maximum temperature. So what you'll see is you'll see the temperature increase, and it will stop increasing, and it'll start to go back down. So once you reach that obvious maximum, write that down. That's going to be your change in heat, your T final, in other words. Okay, so they're asking you to take an image and put it with the report sheet, and then use the data to calculate delta T for the hot water, delta T for the cold water, and delta T for the calorimeter. So the delta T of the cold water will be equal to the delta T of the calorimeter, since we know that the calorimeter and the cold water were the same temperature before we added the hot water. So we can say that delta T of cold water is equal to delta T of the calorimeter. Okay, so after we know delta T of hot water, delta T of cold water, and delta T of the calorimeter, we're going to want to calculate the specific heat of the calorimeter. So how are we going to do that? This might be a place where you get stuck. So I really want to go over this with you to make sure that you get this part. So we're going to use this relationship. We're going to say that Q of the hot water plus Q of the cold water plus Q of the calorimeter has to be equal to 0. And so what we know is that any heat lost by the hot water had to be absorbed by the cold water and the calorimeter. So that means I can rewrite this equation to be Q hot is equal to Q cold plus Q cal. Okay, so I could write this instead. So just subtracting. So minus Q hot is equal to Q cold plus Q cal. Why minus? Because we need to keep the equation true, right? So in other words, anything being lost by the hot water was absorbed by the cold water and the calorimeter. Okay, so that's our new equation. So you probably want to write that one down because it's not in this sheet. Now, what am I going to do with that? So I will then come back up to my calculations here. So I know that, again, Q reaction is equal to Q solution plus Q cal. We're kind of using that equation, but not for this in particular. What we're going to be doing here is using this Q solution. Okay, so Q solution, we're going to calculate one for the hot water, one for the cold water, and then what we'll be left with is Q cal, or so for the calorimeter. So if we know the mass of the hot water, and we know the mass of the cold water, and remember, these are separate equations. So in both cases, we measured 50 ml. We're assuming the density is 1, so we have 50 grams. Times specific heat of water times delta T. Okay, so if we do this equation for the hot water and for the cold water, then we can plug those back into our equation that we just came up with. Okay, so minus Q hot is equal to Q cold plus Q cal. So if we just solve this equation for Q cal, in other words, we combined, so we combine, so we're going to want to combine Q hot and Q cold. So basically you want to subtract the Q cold from the Q hot. So This equation is a little bit misleading, and I want to make sure that I cover that because I kind of misled you a little bit. So essentially, you just want to subtract Q cold from Q hot. But the reason we can do that is because of this equation, but we're not necessarily using this equation to solve for that, if that makes any sense. Okay, so subtract Q cold from Q hot, and anything that's left over will be equal to Q cal. So anything that's left over will be equal to Q cal. And now we can come back to our equation for Q cal. We know that Q cal is equal to the heat capacity of the calorimeter and delta T. Okay, so now just divide by delta T, and that will give you the heat capacity of the calorimeter. Another way we could do this is that since we know the mass of the calorimeter, we know the change in temperature of the calorimeter, but we don't know C of the calorimeter, but we do know Q of the calorimeter. We could also plug into this equation and get the specific heat. It didn't ask you for that. Okay, so that's how you would find the specific heat of the calorimeter. But if we want to know the actual heat capacity of the calorimeter, we need to use this equation. Okay, so the next part of the experiment, you'll be doing the same thing, but with pennies this time. Okay, so now this time we'll know the heat capacity of the calorimeter, so that makes our life a little bit easier. Okay, so with that, we can accurately calculate the heat exchange from the pennies. Okay, so the first thing you'll do is you will use a 250 ml beaker to heat approximately 100 ml of boiling water, or of water to a boil. Okay, and then while the water is heating, you'll do steps 4 through 7, so we'll jump to that in a second. But you want to weigh out 10 pennies and record the mass on the data sheet, and place the 10 pennies into the heating water. Okay, then you want to dry the styrofoam cup and from the home calorimeter. Place 75 ml of water into the calorimeter. Obtain the mass of the assembled calorimeter with the 75 ml of cold water. Measure the temperature of the cold water. Let it stabilize for 10 minutes, so similar to what we did before. Measure the temperature of the boiling water and record that. And then carefully pour the hot pennies into the calorimeter. Okay, so notice that here it says pour the hot pennies. We don't want to actually pour the hot water. So we need to essentially scoop the hot pennies out with a spoon or some other implement. Or we can pour the hot water out quickly and then add the pennies that way. So you can discard the hot water and then pour the pennies that way, or kind of scoop them out. Either way will be fine. Just be careful however you do it. Okay, and then swirl the water with the calorimeter while recording the temperature every 10 seconds for 1 minute. Determine the maximum temperature of the water. Then you want to use this data to calculate delta T of the pennies, delta T of the cold water, and then eventually C of the pennies. So the C of the calorimeter will be used to calculate Q of the calorimeter. Okay, so it wants you to take an image and then remove the cover, and then recover your pennies. Okay, so the process here will be very similar to what we did before. So just remember that if we're talking about big C, we need to use the heat capacity. If it's little c, it's specific heat. Okay, so there's a difference in those two equations. So the calculations are basically the same, so I won't go over them again here, but please feel free to ask me any questions if you get stuck on this part. Hopefully you won't have too much trouble. You don't need to do this acid-base portion. We're going to go ahead and skip that since it's essentially the same thing. I'd rather just not do that for this time around. Okay, again, please let me know if you have any trouble. I will be around at office hours, and I am available through email.